also didn't want to tinker with the quiz while it's going on. So I will, we'll work. I mean, we'll sort it out. Okay? I just need to. Okay. And there was some other question about some rank of some matrix. So I will answer your email either in bulk or individually in a day or two. If you don't hear from me by Thursday morning, please remind me. Okay? I will need to go through the quiz for each student and see what the issue was. I didn't see any rendering problem when I uploaded the quiz, so I didn't spot. I mean, I couldn't spot it. Okay. So I will take. I mean, I will look into it. If you don't hear from me in 2 days, please do let me know. Okay. So yeah. What is, somebody say something?
So we're supposed to email to your CMI mail, right?
Yeah.
Okay.
Yeah. Yes. If you sent it already, I've already received it and saved it. But yeah.
Sir, I sent it from my Gmail account.
If you can just resend it from CMI account, it will be helpful. I cannot keep track of. I agree that from your phone, if you're sending it, it may go from your Gmail account. But if you can just reconfirm it from your CMI account, it will be helpful. I cannot. Okay, please, yeah. I cannot keep track of people's Gmail or Yahoo or account. So yeah. I understand that since I asked you to do it quickly from your phone, or which is what you probably did. It may have come from whatever account your phone is connected to. That is okay, but please reconfirm from your CMI account. Yeah. So actually, one issue I agree that this thing of bilinear forms. We're not going to see any immediate application. Okay? It is not like at least there is a conceptual reason. At least when we are discussing diagonalization or Jordan canonical form, maybe there is a conceptual justification as to why we were doing those things. Okay, but I admit that for bilinear forms, it is probably not clear at all why we are doing or proving all these statements or making these definitions. My personal, I mean, the sort of difficulty is that to see applications of this, at least the applications that I know, they typically come in calculus. When one studies tangent spaces and that sort of things, okay? Manifolds. That's where at least I know where you see the first sort of applications. Okay, and it is difficult. I mean, I know it is not very nice for me to say you should study these things because you will need it in your third semester. But please bear with me. Okay? It is not easy. I mean, it is not practical for me to both do the, or for any instructor, do the theorems now and then also talk about the applications without developing some calculus along the side. Okay? At least okay. So for that reason, this section, I mean, this chapter on bilinear forms may just look very sort of artificial and just came up with some definitions and proved some theorems without even explaining the context. I mean, I agree that is a. I mean, but the problem is that the sort of applications of this come, I mean, the sort of application that I know, or this thing, they come in calculus, which you will see, and the study of manifolds, for which you'll have to wait 1 or 2 more semesters to sort of understand those things. Okay, so that is the sort of an issue. Okay, so but I will try. So in my next lecture, I will try to do a basic example of why these things will come in handy later. Okay, but again, I will not be able to get into lots of details of that example, precisely because those things are typically discussed after you after you study a little bit about multivariable calculus and this idea of tangent space, etc. So, but at least I will try to do the basics of such an example. Maybe if not in the next lecture, but by next Tuesday. Okay? So in the next 2 lectures, I will spend 1 lecture doing this, or at least part of 1 lecture doing a reasonably good example, which should tell you why we worry about these bilinear forms and things like that. Okay, so just to maybe just to give an idea. See, the idea is that this bilinear form given by the symmetric bilinear form given by the identity matrix measures the length of a vector. I mean, it is used to compute the length of a vector. Right? I mean, if you take V transpose identity V, we would just get the length of the vector, a square of the length of vector. Right? So it is to sort of capture the notion of a length that one place where you will have to worry about symmetric bilinear forms. Okay? Well, symmetric bilinear positive definite forms. Okay? Then there are other applications. So the entire thing can be made sense only after you study a few more things. But yeah, so I with due apologies, I say please study this now. You will need it in the future. Okay? So I know it is a bad justification, but okay, so please okay. Yeah. Okay. So we were discussing this notion of orthogonality. Let me just quickly recap from last lecture. So we say that two vectors are, so V is a real vector space with a symmetric bilinear form, or a complex vector space with a Hermitian bilinear form. And V is said to be orthogonal to W if we say that V is orthogonal to W if this is 0. So this agrees with our notion of orthogonality in the usual Rn. This is okay. So then we talked about various things. We can talk about, so if W is a subspace of V, okay, then W perp is the set of all vectors V in V such that V is orthogonal to W for all W. And we saw examples where W perp need not be disjoint from, I mean, may contain non-zero vectors of W. Okay? It depends on the form. Okay? So this is what is called W perp. Okay? The null space of is V perp, which is the set of vectors V in V such that V is perpendicular to W for all W in V. So in last class we saw examples where this is the null space could be non-trivial. Okay? And we say that it is non-degenerate if its null space is 0, in other words, given any non-zero vector, there is a W such that V is not perpendicular to W. So VW is non-zero. Okay? So non-degenerate. And we can also talk about non-degeneracy on subspaces, and we saw examples of those things. Okay? And we also, I also stated the lemma, which I left as an exercise, which is that this is non-degenerate on W. This is W is inside V subspace. Okay? This is a way of, I mean, this is saying that if you take non-zero vectors, I mean vectors inside little v inside W, then there is no little w inside W such that V is perpendicular to W. Okay? This is if and only if W intersect W perp. This is just saying, but see, W see when we, so there is W inside V. We can talk about the bilinear form, symmetric or Hermitian as the cases, on W. But when we say W perp, it is always with respect to the ambient space. Okay, so notice it is always those vectors in V such that V is perpendicular to W for all W inside W. Okay. So this W is W has the bilinear form on itself, but when you talk about the perp, it is always in the ambient space. So this is where we stopped last time. Okay. Okay, so proposition. So let's say this is, let this be symmetric or Hermitian or Hermitian. So if you're discussing complex vector spaces, we are talking about Hermitian. Otherwise, you're talking for real vector spaces, we are talking about symmetric. Okay, on V, form on V. And V and V prime, V vectors inside V. So this is a non-degenerate form. If V W is equal to V prime W for all W inside V, then V is equal to V prime. Okay. So again, for sort of understanding the context, one should probably think about this in the Euclidean space. I mean, the usual Rn. I should not use the word Euclidean yet, okay, but in the usual space Rn with the usual dot product. Okay. So there the statement is true, right? If you have, first of all, the usual dot product is given by the identity matrix, and it is positive definite, okay, non-degenerate, and non-degenerate. Sorry, there is a missing hypothesis here, non-degenerate. Yeah, it is. So the usual dot product, okay, so maybe I should just write remark. Okay, so this is a generalization of the similar property for dot product on Rn. What does it say? If we have two vectors V and V prime inside Rn, okay, they are equal if and only if their dot product with any vector is equal. That is, okay, that is for all V prime inside Rn, V is equal to V prime if and only if the dot product with W gives the same value for V prime for all W inside Rn. Okay. In a sort of very concrete way, we can just take W to be E1, E2 up to En, and then this will just pick out the ith. Okay. So in fact, just need to do V dot Ei. I mean, so this is, maybe I should not write since I said V perp W, not V, V transpose W equals V prime transpose W for all W. In fact, it's enough to check the following, whether
It
V
follows
transpose.
It follows from the linearity and the last lemma, right? This property.
this proposition?
Is what?
It follows from the lemma and the linearity
Yeah,
of bilingual.
no, we will come to the proof. Let me explain the context. We will come to the proof.
Okay.
I'm not leaving the proof as an exercise. Sorry, I should have said that. I just wanted to say where. So we transpose Ej for all 1 less than j less than n. If you do this, then if these are equal for all the Ej's, then it will be equal for all the W's. That is by linearity. And then, yeah, but what is this? I mean, why is it enough to look for this one? This is the jth coordinate of V, and this is the jth coordinate of V prime. Okay, so if the two coordinates, I mean, if the jth coordinate of V equals the jth coordinate of V prime for every j, then V prime is equal to V equals V prime. Okay, and that's what is P. Okay, so this is the, I mean, this is where the proposition comes from. So we'll now prove it. Proof is not difficult at all, but just to understand, see, most of the time these this idea of bilinear forms is introduced to generalize this notion of dot product and to talk about some notion of length and notion of orthogonality, okay, to introduce these things in a more general context. Okay, so that's why these things, I mean, this one studies these things. And so okay, so that's okay, so just to understand the context of where the proposition came from. So proof of proposition. Okay. Yeah, so yes, indeed, the previous lemma is used in this one. So suppose V W equals V prime W. Okay. I mean, for some W, for every W, whatever. Okay, what does this say? Okay. So this says that V minus V prime W is 0. Okay. Or in other words, that is, just restating it, V minus V prime is orthogonal to W. Okay. That's what equality of these two things mean. In fact, I mean, this is equivalent. Right? Vanishing of this thing, V minus W, product of V minus W with W, V minus V prime with W is equivalent to the equality of these two things. Okay. So now let us, yeah, so but what does this mean? Therefore, VW equals V prime W for all W inside V implies that V minus V prime is inside V perp, but V is non-degenerate. Okay, this is a null vector, so this is non-degenerate. Okay. So this means that V minus V prime is 0, since this thing is non-degenerate. Okay. On V. Okay. This is what we wanted. V equals V. Okay. So this is yeah, this is what we need. This is what versus said. Okay. So proposition. So yeah, again, so let us look at another proposition. So most of this is just to identify V perp, the null space, or W perp for some W, etc. Yeah. So let be a symmetric or Hermitian form on V. Again, the symmetric versus Hermitian dichotomy is based on whether V is thought of as a real vector space or a complex vector space. Okay, so if V is a real vector space, we're talking about symmetric forms. If V is a complex vector space, we're talking about Hermitian forms. Let A be the matrix of with respect to a basis. What basis it is not relevant. Okay. Then 1. V is a null vector if and only if its coordinate vector. Okay. So V with respect to the basis can be written as an element of a column vector belonging to some Rn or Cn appropriately. Coordinate vector y. Coordinate vector y satisfies A y equals 0. So this gives us a way to so we and to be 2. The form is non-degenerate if and only if A is invertible. Okay. So and again, just to maybe I should add a couple of remarks, at least one remark. Okay. If A is invertible, and if A prime is the basis, is the matrix of this thing with respect to another basis, okay, then that matrix is also invertible because they are related by some P transpose A P, and P is invertible. Okay. If A prime is the matrix of this thing with respect to some other basis, then there exists invertible P such that A prime is P transpose AP. Okay. Therefore, if A is invertible, then A prime is invertible. Okay, just to this is regarding 2, because in 2, the first part, the form is non-degenerate, does not depend on a choice of basis. While the right side, the matrix depends on the choice of basis. Okay, so in 2, it may sound as if, I mean, one side doesn't depend on basis, others may sound, other side depends, but I'm just clarifying that it doesn't. Okay? So the matrix, whether the matrix is invertible or not, is independent of what basis we try to compute the bilinear the form. Okay? And oh, maybe let me add one more remark before the proof itself. Okay. So this is regarding 2. Okay. I want to add another remark regarding 1. So this, what does AY? AY is just a column vector, right? AY is just a column vector, and just a minute, just AY is a column vector. Therefore, this map X goes to X transpose AY. So take, okay, this function is from therefore the function from Rn so okay, so we didn't sorry, for this discussion we didn't need to know what the dimension is, but for this remark it will help, okay, to R, where n is the dimension of, so I'm just assuming that it's a real vector space. Okay. I mean, for the purpose of this remark, just assume it's a real vector space. It's not relevant, it's just to explain some point. Okay. So just assume that this is a real vector space, that V is a real vector space. I mean, whatever I say will hold in general also. Whatever sorry, was I not audible in a few minutes for you?
Yes.
Okay. Yeah. Whatever I say will hold in general also, but this is just for illustrative purpose. Okay. So assume that. Okay. So now, so I am considering just here. Okay. So X goes to X transpose AY. Okay. This is a linear transformation. Therefore, is a linear transformation. Okay. That is easy to check. As we add or scalar multiply X, the same thing will show up on the right side also. Okay. So it is a linear transformation. In fact, this is the linear transformation.
Sir, you are defining this function, right? I mean,
yeah,
according
I'm
to the rule.
function. Yes,
Okay,
X is the X is an element. Yeah, correct. I am defining a function from Rn to R by sending a vector X to X transpose AY. Y is given. Y is given. So, okay, okay. I should not say Y is given, but correct. So let Rn. Okay. Then AY is a column vector inside. I mean, it's inside Rn. So this gives a linear transformation. This is what. Now, what linear transformation is this? Okay. This is the same linear transformation. Just a minute, I think I. Yeah, okay. This is the same linear transformation. V goes to R. Okay. Some vector W goes to WV. Okay, where this thing corresponds to Y in the given coordinates. Okay. I mean, we saw the definition of a bilinear map is that on any single okay, so that okay, a bilinear, this is now linear bilinear for real vector spaces. Okay. So the bilinear map is from V cross V to R. I mean, the form is from V cross V to R. Okay, but if you fix a second coordinate, which is what we are doing here, fix V or equivalently fix Y in the matrix form. Okay. Then W going to this thing, or in other words, X going to X transpose AY is a linear transformation. Sorry, did somebody have a question? Hello? Am I audible?
Yes,
Yes,
sir.
sir.
I don't think so.
Okay, sorry. I thought somebody had a question. Sorry. Okay. So then this is the same linear transformation as this one. As V going to, okay. So this is just, okay. So what is this saying? So AY, if AY is the zero matrix, okay, then this form is non-degenerate. Okay. And if this linear, whether vector V is a null vector or not, okay, is determined by whether this matrix AY is whether this linear transformation is trivial or not. Okay, so let me just call this thing linear transformation psi. Okay, so so I'm just rewriting in some sense one. Therefore, what one says is that the form is non-degenerate if an sorry, non-form is degenerate. That V is a null vector of the form is that V is a null vector of the form if and only if psi is the zero linear transformation. Okay. Okay. So this is what is saying. Just to understand the statement a little bit. Okay. I mean, we will prove it. Proof is not very difficult at all. But just to make sure that we understand the statement. Okay. So proof of proposition. Okay. So using this basis, okay, we can think of the form as X conjugate transpose A Y. Okay. So if you are in the real situation, this conjugate transpose just means transpose. Not the form. Maybe I should just call it something else. Some X relate transpose A X prime. Okay, where X prime X and X prime are column vectors. Okay, in Rn or Cn as appropriate. Okay. It is still fine to write X star because if you're discussing real numbers, star just means, I mean, real vector star just means transpose. No conjugation doesn't do it. Okay, so this is okay, so X and X star are called where. Okay, so this is the okay. So now yeah. So now suppose that AY is 0. Y is the coordinate vector of V. Okay, suppose this is 0. Okay. then X transpose A, X conjugate transpose AY is 0 for all X inside, for all X. Okay, let me leave it ambiguous as to whether it is inside Rn or Cn, but take the appropriate case. This is 0 for all X, which means that V is perpendicular to W, V corresponds to Y and W corresponds to X for all X, for all W inside V, which is the same statement that V is inside the null space. Okay. Conversely, okay, if V is in the null space, okay, this is by definition that sorry, forget the last thing. V is a null space means V is orthogonal to W for every W. Or maybe I should write just for it is a symmetric form, so I can write, but just to be precise, maybe let us write okay. W is perpendicular to V. Yeah, at least that's the way it is written. It is a symmetric form, so yeah, it's either a real symmetric form or a complex Hermitian form, and the question of whether if it's in the complex case, whether V is perpendicular to W, that condition is symmetric. I mean, V is perpendicular to W if and only if W is perpendicular to V. Okay, so we get this condition. Okay, so now this says X star. Okay, so what we have proved is that X star AY is equal to 0 for all Y is the condition that we are looking for. Okay, so let me just write conversely. Okay, following the
Sir,
green
but
arrow.
where did we use exactly that it is a symmetric or Hermitian form?
Where did you use? Well, the notion of perpendicular is only defined for symmetric and Hermitian forms. See, otherwise it could be that I mean, sorry, I will erase whatever I'm writing. This is not. See, if this is not, say, is not symmetric or Hermitian, okay, then it is possible that this is 0, but if you do it the other way around, it is not 0, right? For some VW, right? So when we discuss orthogonal, I mean the notion of orthogonal vectors, it is always, I mean, at least the way we are discussing it is always with respect to symmetric or Hermitian form. Does that answer your question?
Sir, but V, I mean, the inner product V comma W is equal to W comma V in real case.
No.
Oh,
Just
okay.
For the
Yes,
dot
sir.
product, that is
Yes,
an example
yes.
of a symmetric bilinear form.
Yes, sir. Yes, sir.
Yeah. Yeah. So in general, whether it should hold or not, yeah, that is. So following the green arrows, okay, up backwards, okay, what we need to show that AY, that if this holds, the X star AY is 0 for all X, then AY is 0. AY is 0 if X star AY is 0 for all X. Okay, X in Cn or Rn. Okay. But this is again, okay. So take X to be E1 up to En, standard basis. Okay. Then X star is again just okay. So maybe I shall be more precise. Let J be between 1 and n, and take X to be Ej. That is jth standard basis vector. Then X star is just Ej transpose.
Sir,
Yeah,
so could you scroll up a bit?
yeah.
Okay, so just a minute.
Yeah, sure.
Yes, sir. Yeah.
And so X star is Ej, therefore, and X star, therefore, X star Ay is the jth coordinate of Ay. Okay. Therefore, if that is 0 for all X, for all J, okay, if therefore, if X star Ay is 0 for all X, then Ay is 0, because it would imply that the jth coordinate of Ay is 0, therefore for every J, and therefore Ay is 0. So B is a corollary to this. Okay. Form is degenerate if and only if the null space is 0, if and only if for all y, Ay is not 0. That is the condition which puts it for all y not equal to 0, Ay is not equal to 0. Which is the condition which says that no non-zero vector is in the null space, which is the condition that A is inverted.
So you mean non-degenerate, right?
Oh, sorry. Correct. Non-degenerate. This- okay. So this is a slightly important result. So the one thing to keep in mind is that almost all the proofs are actually, you would have noticed, almost all the proofs are actually done with concrete calculations on the matrix, using the matrix A, which represents the thing. And the intuition for these statements come from how the usual dot product or the standard Hermitian form works in the two cases. Okay, here. As usual, this is a symmetric or Hermitian be a symmetric or Hermitian form on. This is again just to emphasize. This is if you're discussing real vector spaces. This is if you're discussing complex vector spaces. Okay, on V, and let W be a subspace of first statement. The form is non-degenerate on W. W, if and only if V is the direct sum of W with W perp. Okay. And 2, if the form is non-degenerate on V and on W, then it is non-degenerate on W perp. So again, just to put things in context, see, earlier, see, given some sort of, so in the, so till when we were discussing Jordan diagonalization or Jordan canonical form, what we had was a linear transformation acting on some vector space V, and we wanted to check if V can be written as a direct sum corresponding to eigenspaces or generalized eigenspaces. So this is this is something that we often try. The reason is that then it is enough. So if we know to decompose a space, or if we know that given some linear transformation on V, we can decompose V into some individual, separate subspaces, so whose direct sum, so that V can be written as its direct sum based on some data coming from this linear transformation. Okay? Then it's easier to study the linear transformation because you just have to study on each individual summands in the direct sum. In the case of diagonalization, or more generally in the situation for Jordan canonical form, we decomposed it into the generalized eigenspaces. So therefore, we just have to study for the linear transformation on this direct summand corresponding to a fixed generalized eigenvalue, and on that it looks nice, etc., etc. Okay, so this is okay. So here we are doing something similar, which is to say that based on so that I want to write. Okay, so I will write now. So remark. The idea is to check whether V can be decomposed into some as a direct sum where for each I different from J, Vi is orthogonal to Vj. In other words, every vector that is V is perpendicular to W for all V inside Vi and for all W inside Vj. Okay. So V has a nice decomposition coming from this bilinear form. earlier we did, I mean, sort of something philosophically same, which is to understand whether V has a decomposition from, I mean, coming from the given linear transformation. So here we are doing something similar. Okay, so this is, if such a thing exists, we'll say that this is an orthogonal sum of subspaces. If such a decomposition exists. Okay. We say that V is an orthogonal sum of subspaces. I mean, of the subspaces. V1 through.
So here M is anything less than the dimension, right?
You know, yeah. I mean, no. We're not asking whether for every M such a decomposition exists. Yes, M has to be less than the dimension, because otherwise, you know.
So I mean, we are not looking for a basis. I mean,
No.
orthogonal basis.
We're not looking. No,
till
right now we're not looking for any of those things.
Okay. Okay. Yes.
We are just asking, and we're just asking whether, given this, this thing, whether we can write, write it like this. Yeah, I agree. We're not asking for, yeah, we're not looking for a basis. I mean, we will eventually get to. We'll prove various things related to orthogonal decomposition. But right now, I'm just saying that, I mean, this is the, I mean, to understand this question, I mean, that is the motivation for this theorem. It gives a sufficient condition or a necessary condition for V to be able to write V as W direct sum W perp. Okay. This is. Okay. So this is, yeah. So I'm just sort of explaining the context, not exactly proving anything about with the existence of such decomposition. Proof. Sorry, did I make more statements? Correct. Okay. Yeah. So let us first suppose that V is the direct sum. Yeah. So this in particular implies that W intersect W perp is the zero vector. This means that the form is non-degenerate. On W, right? Any vector that has to be that is perpendicular to every vector in W is a zero vector. Zero vector is the only vector that is perpendicular to everything in W. So therefore, it is non-degenerate. That is just, this was the lemma. Okay. So we need to prove. Okay. So now, conversely, suppose that W, the form is non-degenerate on W. Then W is, of course, this is zero. Okay. Yeah. So this, yeah. So therefore, what we need to show, therefore, to show that V is W direct sum W perp, okay, we need to show that V is W plus W perp. That is, okay, for every V inside V, there exists W inside W and U inside W perp such that V is W plus. Okay. What we need to show. Just hold for a minute.
No, sir. Yeah, now it's visible.
Sorry, I got. So I was talking about. I was saying this. So suppose that this is non-degenerate on W. Okay, then W intersect W perp is trivial. Therefore, to show that this is a direct sum, we need to show that V can be written like this. Okay, for every little V in V, there's a W in W and U in W perp such that little V equals W plus U. Okay, so this is what we will show now. So let K be the dimension of W and W1 through WK be a basis of W. Extend it.
Can't we just consider the projection of W and W perpendicular? Then show.
What is projection?
That projection, like with respect to the form.
But that we have not proved anything, right?
Okay.
Yes, we are getting there. Yes. Yeah. I mean, but that, yes, that okay. Extend it to a basis. But we still don't know if their dimensions are complementary. That is essentially that is the content of the proof, right? I mean, even if we knew how to project with respect to a form onto a subspace, which we have not developed anyway, but if we knew that, we still don't know that the dimensions are complementary.
Both are subspaces and they do not intersect. So
yes, that doesn't mean they're complement. Their dimensions add up to the whole space, right?
Yes.
I mean, it is true in Rn or Cn, the usual notion of orthogonality, but one needs to prove it in this generality, right? Extend it to a basis B, which is these K1s and then some Vk plus 1 through Vn of V. And so if we can show that we can choose Vk plus 1 through Vn from W perp, then okay, we can conclude that conclude that V is W plus W perp, right? Because the basis elements of V come from W union some basis elements for W perp. Okay. So therefore, V will be inside W plus W perp, but they are both, I mean, what we will really see is that V is inside W plus W perp. I mean, if you show this, this is what we can conclude, but this is of course inside V. So both are subspaces of V, so there's sum is also subspace of V. Okay. And that is okay. Yeah. Okay. So this is what we can conclude. Okay. So now, so we'll have to do some manipulation to show that we can choose this with respect to this basis. Okay. Okay. So again, the actual manipulation is on some matrix. So I will redo that part next lecture again because it's a little tricky. So I'll just outline it now. We'll go through the details in the next lecture. Okay. Yeah. So I mean, we will not actually manipulate V1 through Vk plus 1 through Vn. Instead, we will just manipulate a matrix in a way knowing that this amounts to manipulating Vk through Vn. Okay. So let M, so this is a matrix, n by n. There is a matrix A, which is k by k, and then call it B, C, and D. Okay. Be the matrix of the form on V. Okay. And where, so in this, here, A, the k by k matrix, is the matrix of the form on W. This is with respect to this basis. W1 through WK, VK plus 1 through Vn. So this W1K so WK was chosen to be basis for W. Rest was just taken inside V, but we want to show that they can be taken inside W perp. That's the goal. Okay. So A is the matrix on W with respect to this basis. Okay. Therefore, by earlier proposition, A is invertible. Okay. Now, what are the entries of B? B are okay, Wi with Vj. Okay. 1 less than or equal to I less than or equal to k, and k plus 1 less than or equal to n. Sorry, yeah, I don't know why I call them Vk plus 1 through Vn. If you like, you can call them V1 through Vn minus k. So this is the I comma jth entry of the matrix M, which just belongs to B. I comma j with this. Okay, so this is the ijth entry of, okay, and that just belongs to B. Okay. So what we want to show is that, okay, so we want to choose Vj from W perp, or okay, choose Vj from W perp. We would like to, if they are not from W perp already, we would like to do some change of basis so that the new ones are from W perp. So more precisely, okay, if Vk plus 1 through Vn are not from W perp, are not all from W perp, even if one of them is outside, then we would like to do a change of coordinates of V, okay, to get a new basis. Change of basis is probably better. A change of basis, but keep the first k ones fixed, because we want them to come from W. Okay? W and some V prime k plus 1 through V prime n, such that V prime j is inside W perp for all k plus 1 less than or equal to j less than or equal to n. So what time is it? Okay, I'll just quickly finish. I think it's all. Okay, yeah.
Okay.
I just quickly, anyway, I'm just going to, this is only a philosophical outline of what we're going to do. The details, we'll have to work it out. Okay. But what does a change of basis of V do to the matrix M? So we'll just manipulate the matrix M, knowing that this actually corresponds to K. So this replaces M by a matrix of the form P transpose M P. A change of basis for the vector space corresponds to a transformation like this for the matrix when we are discussing bilinear forms, okay, where P is an invertible. Okay, so what we will show is that there exists such a P, there exists invertible P, P transpose MP, or or P MP in the complex case. I should just write P in the complex case. Okay, I should just write a P conjugate transpose. Will take care of both. There exists an invertible P, okay, such that, okay, such that whatever we want will hold, which is such that P conjugate transpose MP is of the form A 0, okay, and some D prime, not necessarily the old D, okay, but see, this is a symmetric or Hermitian form. So if the off diagonal entries like this are 0, then we'll get 0 here also. I mean, this 0, once we make the B go to 0, the C will also go to 0. Okay, so this is okay. So this is what we will show. So this we will do in the next class. Okay, so just read this, because the actual manipulation is just to find such a matrix and saying that this solves the problem. Okay, but you must understand why it solves the problem, which is what I have tried to explain now. Okay,
will it Gram-Schmidt orthogonalization for inner product in SEM 1? So we can apply that like on the form instead of the inner product, and to find those.
Okay, sorry. I didn't actually check what you learned the last semester. I was going to redo this whole thing again. So yeah.
I mean, just the Gram-Schmidt orthogonalization process, we just construct, take a vector and then construct the orthogonal elements. So now we take W and.
But for what vector spaces? If I understood correctly, what Professor Ramdas did was, he told me that he did only a sketch of things for real vector space.
Yes.
Yeah, but that you can't apply for complex vector spaces now, right? Without proof.
Yes.
Yes.
I mean,
Yeah.
the idea will be similar lengths.
No. I am not questioning the idea. I'm just saying we
Yeah.
have to prove something. We have to develop it one step at a time. So yeah. I agree. But so this is what Professor Ramdas said. So I was just going to redo everything from scratch without assuming that you've seen anything of this earlier. Okay. Yeah. So from what I understood, he had only done the real case, and that too, some of the topics he said he only sketched because he ran out of time or something. So I will, yeah, I agree. I mean, this is completely, I mean, this is sort of related to Graham Schmidt, but without proving those things properly, we cannot just apply it here. Yeah. Okay, I'll stop here.
Thank you, sir.
Thank you, sir.